Well, again, I try to share the full screen so that you see not only the slides but also the notes, and we will cover both the slides and the notes so that we make sure that everything has been covered. Well, as we mentioned previously, we talked about the hydrogels, but we didn't mention about the mechanical properties of the gels. Well, when we are talking about the gels, we need at least two phases, one the liquid and the second one as the solid. Well, in the matter of hydrogels, the liquid phase is for sure is water, but the solid phase is mainly the polymers, which are going to be cross-linked. Not only the cross-linking between the polymers can form the gels, but also increasing the volume fraction, if you remember, can form the colloid gels, but we don't deal with them now. We're just going to deal with the time that the polymers are going to cross-link to form a network. This is the essential part of the gels that we are going to deal with. So anyway, comparing the mechanical properties of a gel with the solid and with the liquid, if you remember in the introduction in the previous video, I mentioned that the solids, when they are under stress, they show the deformation based on the G prime. This G prime is called the elasticity. Let me find it for you. It's here, the elasticity effect. On the other hand, for the liquids, we will deal with the viscosity. So how about the hydrogels? For the hydrogels, we will define the mechanical properties by the name of viscoelasticity. So not only they are viscose, it means that they contain the liquid phase, but also they are elastic, which means that they show some solid properties. Okay, this is the rheometer that I mentioned in the introduction. We have this oscillating plate which applies a sinusoidal stress on our material, and you see here this black line is the stress which has been applied, but on the other hand this dashed line is showing the amount of the strain, the deformation associated with this black line, with the stress. So this is the stress that we have applied, and this is the strain, the deformation that happened. If you remember, in the introduction I mentioned that the ratio between the stress and the strain defined the modulus for us, and we are going to use the ratio between the stress and the strain to measure the amount of modulus for the hydrogels. But let's continue with this slide. In the first case, just consider a solid. When we have a solid, if you remember, the ratio was linear. Let me show you again. Here I mean the ratio between the stress that was applied and the strain which was obtained was linear. So as it can be seen here, you see that between the function of the stress, the behavior of the stress and the behavior of the strain, this stress and the strain, there is no phase difference. You see here that the phase difference is equal to 0. However, for the viscous fluids, if you consider this as the stress, you see here that there is a phase difference between the stress and the strain. It means that at the time that we apply the stress, sometimes later the strain is let's say is obtained. Okay, so it shows us the phase difference between the stress and strain for the fluids, and it's equal to 90 degrees. However, for the hydrogels, which show the viscoelastic properties, you see here this purple line, that it is something between these two, the phase difference between the zero in the case of solids and 90 degrees for the case of viscous fluids. So let's go a little bit into mathematics. You remember that above I told you that we are applying a sinusoidal stress, and this sinusoidal stress, it's here. You see here that it has the frequency of omega t, and also this sigma 0 as the maximum value of the stress which is applied. But here that we are dealing with the mathematics, for just simplicity, we consider the cos function of the frequency, and you see here that for the viscoelastic materials, when we apply the stress with this frequency, the strain which is obtained has a phase difference. So what we are going to do, we are going to just simply calculate the ratio between the stress and the strain. Well, I don't want to give you really a lot of details about the mathematics that happened here, but let's just make it quick, and let's just consider that if you know this this law of mathematics, you know that the real part of this function shows the stress that we have applied, and the real part of this expression will show us the strain that we have applied. If we take the ratio between these two, we will reach into something like that, as you see here. So the ratio between the stress and the strain which has been applied, and we will finally lead to this number with the phase different, this phase different. And when we again use that mathematical expression here that we have, we will reach to a real part and an imaginary part. This real part we call it G prime, and this imaginary part we call it G double prime. I know that I proceeded a little bit quickly about these mathematics, but I just wanted to show you that when we divide, when we measure the ratio between the stress and the strain of the viscoelastic materials, the modulus is sum of two parts, a real part and an imaginary part. This real part is the one related to the solid phase, and this G double prime, the imaginary part, is corresponding to the liquid phase. As you see here in the notes, if you wanted to study, I have written that this term is this G double prime is not going to be present when we are considering the ideal solids. So it is crystal clear, it is obvious. When we have a solid, we have only this real part. On the other hand, when we have a liquid, we have only this part. But for the viscoelastic materials, both of them are present. So it shows us how viscous the material is. This is called the viscous modulus, and it shows us how elastic the material is. It is called the elastic modulus. So let's just continue, and you see here that the G prime is a real number and the G double prime is an imaginary number. So the overall modulus, the G star, which is defined for the viscoelastic materials, is a complex modulus. So this is something obvious. Well, here is the diagram that I showed you in the introduction, and I told you, consider a condition in which the cross-linking between the polymers is increasing by time over and over again. So at this point you see here that the G prime is lower than the G double prime. So it tells us that the system that are let's say the comparison between the solid phase and the liquid phase tells us that the liquid phase is winning over the solid phase. But as the time goes by and as the cross-linking between the polymers is increasing, at some point the modulus of the solid and the liquids become equal. And as the time increases more and more, the G prime increases and takes over the G double prime, and we have the gel. This point where the two moduli are equal, this is called the gelation point. And as we increase the let's say cross-linking between the polymer chains, the elastic modulus will become dominant and it will increase due to the cross-linking of the polymers in the system. And after that we reach into a plateau. You see here that there is no increase in the G prime. This is because we have reached into the maximum, let's say, cross-linking possible. Well, for this slide I have to zoom a little bit so that you see all the details. Well, let's have a look at this part. Well, we have the polymer chains, and these polymer chains have the, let's say, methacrylates. They contain the double bonds, and we also have the files in the system which can be used to connect them to each other. If you remember, in the bioconjugation I told you that we can conjugate the files into the double bonds, the olefins, by using the Michael type addition. So when the cross-linking between these polymer chains happen, you see here that the amount of G prime is increasing more and more until it becomes greater than this black line. So the G prime becomes greater than the G double prime, and this is the gelation point. And as the time goes by cross-linking more and more these polymers, the G prime will increases more and more, so the elastic behavior of our gels is increasing. However, you see here that we have the also possibility to perform the free radical polymerization to cross-link even more and more of these polymeric chains with each other to increase even G prime more compared to this red line. This is the time that by having the radicals and the initiators, this cross-linking will also give us larger elastic modulus in our hydrogels, or let's say in our gels. And remember that this increase that I showed you is just because of the cross-linking of the unreacted parts that had not react within the Michael type addition that we had here. Anyway, let's go to the next slide, and I have to again zoom in to make sure that I cover everything for you and you see all the details. Well, we have a diagram here which shows us on the vertical axis the temperature, and on the horizontal axis the concentration, and it tells us that if we use the pluronic polymers, as you see here, these polymers are amphiphilic. They contain a hydrophobic part, this PPG, and the hydrophilic parts, the PEG, polyethylene glycol, and they are able to form the micelles. So if we consider on this horizontal axis, you see here that first of all we only have the liquids and there is no micelle. Here in this region between, we have the colloids, we have the micelles which are dispersed into our solvent, and here we have the gels. You see here that if we increase the concentration of the unimers of these pluronic polymers, they will finally form the micelles. On the other hand, if we increase the temperature relatively high, at high temperatures we will have the micelles dispersed in our solvent as well. Well, why do we say high temperature? Because the temperature of our body is about 37, and at this temperature around 45-50, it's a relatively high temperature compared to the temperature of our body. Finally, just consider this behavior. If we try to increase the concentration and the temperature of the pluronic polymers in our sample at the same time, you will see that we will have the gels, and this is something that we can use for tuning the properties of our hydrogels. Just consider if we design the pluronic in a way that by increasing a concentration or the temperature, we can form the gels instantaneously upon the injection. For example, upon the injection, when the temperature is increased to 37, we can just tune the properties to get the hydrogels. But anyway, let me just check if I have covered all about this. Yes, and I just have to remind you that when the gels are formed in this region, we will have the micelles which cannot form, but in this region we have the micelles dispersed in the colloids which still have the ability to move. Well, in this example, you see that again the polyuronic polymers are used, but the difference is that they have four arms, and again they will form the let's say sort of a lattice when they form the hydrogels. Well, uh, before we go to this slide, I have to say something which you will find in the notes here. Let's see what this is. I am really sorry about my bad handwriting, but try your best to read it. Well, the fact is that when we have the hydrogels, the force which attracts the particles or the polymers towards each other to form the gel, this force is a physical force. When we inject our material, we have the physiological fluids around it. So some of the polymer chains will finally detach and diffuse into the fluids. So as the concentration of our polymer network is decreased in our hydrogel, you see here that based on this I showed you that when the concentration is decreased, we will come from the hydrogel into the micelles, which are colloids, which are dispersed into our solution. So we want to stay in this region. Decreasing the concentration is something that we don't want to happen, but let me just come back again. But in this situation, when the polymers are just detached from our hydrogel and they diffuse into the solid, into the fluid around it, you see that the concentration, this C, is decreasing. And when it decreases, we will have a transition to liquid phase, so there will be no gels. And this is a problem for us, and we want to solve this problem. To solve this problem, we can have again the polyuronic polymers, and we can add these acrylate partners to them. Just notice that they have the double bonds as you see here. So what we are going to do now, we want to use the chemical bonds, not only the physical bonds. I told you the problem was because of the physical bonds between the network of polymers. But here we have the double bonds and we have the phylls. So when they react with each other, we will have a network under Michael type addition, which is chemically bonded to each other. So now the concentration will not have the opportunity to be decreased due to the detachment of the polymer chains from our hydrogels when it is let's say injected into this gap, when it fills this gap. I hope that you have understood what I wanted to mean, and we call this process, the tandem process, the process of using the chemical bonds in order to have the hydrogels which are connected to each other more strongly. You see here that first the polymers are going to be connected to each other by the physical bonds. So this is called the physical gelation. When it transforms to this, we have the physical gelation. This physical gelation is quick, but it is not strong. So you see here that I have written the bonds are weak. On the other hand, when these polymers are connected to each other by the chemical linking, we will have the chemical gels, and this is slow compared to the physical gelation. The chemical gelation is slower, but it is stronger. You can see the notes here I have written, so that for the chemical gelation it's slower and it is stronger. What I have written in these notes is just telling you that the time that takes for the physical gelation and the chemical gelation differs, and we want both of them to happen at the same time to prevent the dissolving and to prevent the loss of the loss of our polymer chains when they are injected, to prevent the decrease in concentration. And again, you see here that at the beginning we have the physical gelation. Let me zoom and you see better. We have the physical gelation, so the G prime is increased, and when we have the chemical gelation, it increases even more compared to the physical gelation. And after a sort of time, when all of them are cross-linked, we will reach into the plateau, so it will not increase anymore because all the polymers are now connected to each other, and we have the maximum cross-linking between all the polymers, and the network is packed as possible. Well, let's see how long I have been talking. Okay, I have been talking for 28 minutes, and in the next videos we will see how we can take advantage of this phenomenon. Let me show you here. This increase in the temperature for the formation of the gels to encapsulate these cells into our hydrogels or into our gels. So you will see that we will encapsulate the cells into the gels, and we will cover some applications of this technique. So let's go for the next video.